the Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program is an introduction to composite materials and manufacturing. Composites are made up of at least two distinct intended materials which together improve product performance and/or lower manufacturing costs. Many materials routinely designated by other terms are also considered composites, including plated, clad, or coated metals. The term composite, however, has come to mean a material consisting of a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. The reinforcement's function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles. Both matrix and reinforcement materials can be polymers, metals, ceramics, or carbon. The focus of this program is on the most widely used composite materials, fiber-reinforced thermosetting polymers. Thermosets require curing to develop their full mechanical properties. Once cured or set, thermosets cannot be reprocessed. Some of the primary thermoset matrix materials are polyester, epoxy, bismuth imide, phenolic, and polyimide. The polyester matrix materials are the least strong and the least heat and weather resistant. Within these limits, however, they can be quite versatile. They are also the least costly, thus are used extensively in commercial applications. The epoxy, bismuth imide, phenolic, and polyimide composites provide superior mechanical performance and heat resistance. Reinforcement material can significantly improve mechanical properties, such as strength and rigidity. These improvements are especially pronounced when long-oriented fibers are used. Physical properties, such as density or weight per unit volume, thermal expansion, electrical conductivity, thermal conductivity, and vibration dampening, are also influenced by the reinforcement. Some of the most commonly used fibers are e-glass, aramid, and carbon, which is also referred to as graphite. These fibers come in many forms, with some of the most common being strand, tow, which is a continuous bundle of untwisted filaments, fabric, which is a woven construction of interlaced fibers, filaments, or yarns in specific patterns or weaves, pre-impregnated or pre-preg tape, which is a flat, thin, narrow, and long grouping of parallel filaments held together by the matrix material, and preforms, which are reinforcements formed to various shape prior to use. Several different fiber materials can be used in the production of a single part. Fiber direction can be the same, varied angularly, or varied randomly through part thickness. Fibers and matrices are combined to form a multitude of composite products, often at a significant weight saving and sometimes cost saving relative to traditional materials. For these reasons, many major industries use composite materials, including aircraft, especially in military applications, aerospace, marine, sports equipment, automotive, medical, electrical, and construction. There are numerous methods of producing parts from fiber-reinforced thermoset polymers, with the primary types being manual layup, automated layup, spray-up, filament winding, pultrusion, and resin transfer molding. Manual layup is a widely used method of manufacturing a wide range of composite parts and components. The process begins with cutting the reinforcement material to size. This may be performed using knives, scissors, disc cutters, power shears, rotary power cutters, saws, or lasers. A mold having the desired part shape is then coated with a release agent to permit subsequent part release. Composite manufacturing molds are commonly made of steel, aluminum, nickel, copper, or polymer matrix composites. Once coated with a release agent, a layer of resin called a gel coat may be applied to the mold and allowed to cure to a tacky state. As the gel coat cures, the reinforcement material is prepared for application by impregnation with wet resin or matrix material. The impregnated reinforcement material is then placed on the coated mold surface and hand-rolled for uniform distribution and removal of entrapped air. More reinforcement material and resin are applied as needed in this manner until required part thickness has been built up. This so-called wet layup method can be used with nearly all reinforcement materials and is widely used to produce glass-reinforced polyester products and sometimes glass-reinforced epoxy products. Wet layup is also used for making composite molds. Layup can also be performed using prepreg material. Use of prepreg eliminates separate handling of the reinforcement and resin. Prepreg reduces resin consumption and can improve part quality by providing more consistent control of reinforcement and resin contents. However, prepreg must be kept in refrigerated storage until use time to prevent pre-curing. The automated layup of prepreg material is used primarily in the aerospace industry and is accomplished using tape laying machines and fiber placement machines having computer numerical control. Automatic tape laying machines are programmable gantry-style machines having a Y-axis crossmember, sliding on X-axis ways that supports a multi-axis tape laying head. The head has a spool of paper-backed unidirectionally reinforced tape and cutters to cut the tape without cutting the paper, which is retrieved on another spool. The head also can heat the tape if necessary to develop tackiness. The head deposits rows of tape, butting each row against the edge of the previous one. At the end of each row, the head cuts the tape and moves into position to deposit the next row. There is essentially no limit to the size of workpieces that can be tape rolled, but the shape of the workpiece has to be relatively flat to butt each successive row without gaps, overlaps, or wrinkles. To overcome the limitations of tape layers, automatic, multi-axis fiber placement machines were introduced. The machines automatically control dispensing numerous individual narrow tapes of material, which are collimated as they are laid on the mold surfaces. Each tape can be independently dispensed, clamped, cut, and restarted during fiber placement. As a result, parts of compound curvature with convex and concave surfaces and small bend radii can be produced. With the spray-up method, resin is sprayed onto a prepared mold surface using a specialized spray-up gun. The gun simultaneously chops continuous reinforcement into suitable lengths as it sprays the resin. Fiber reinforcement is mainly chopped E-glass, and it may be accompanied by additional reinforcement such as woven roving. Several styles of guns are available. The resin can be mixed externally or internally within the gun cavity. Spray-up guns can be used in automated systems and consequently allow higher productivity than manual spray-up. After layup, composite parts may be allowed to cure at room temperature or with open-air heat assist. Composite parts are also commonly consolidated and cured in heat-platen presses, ovens, or autoclaves. Curing cycles for composites can be lengthy, ranging from an hour to half a day or longer. The process is typically faster in presses than in ovens or autoclaves, but ovens and autoclaves can accommodate much larger parts or many small ones. Layups may also be consolidated and cured using vacuum bag molding. In vacuum bag molding, a non-adhering plastic film, typically polyester, is sealed around the mold plate and layup material. An air valve or valves is then added to the plastic film for vacuum connections. Once ready, a vacuum is slowly created under the bag formed by the film. This vacuum forces the bag against the layup, drawing out entrapped air and eliminating voids. Additionally, it also draws out excess resin. Once full vacuum is applied, the mold is allowed to cure at room temperature or transferred to an oven or autoclave for curing. Vacuum is usually maintained during the entire heating and cooling cycle. Vacuum bag molding is effective in producing relatively large and complex shaped parts, including those having compound contours. Filament winding involves wrapping a narrow fiber toe or band of toes of resin-impregnated fiber around a mandrel of the shape to be produced. When the mandrel is removed, a hollow shape is the result. Uses for filament winding include pipes, tubes, and fittings, springs, cylindrical, oblong, and spherical pressure vessels, storage tanks, drive shafts, rocket motor cases, and helicopter blades. Filament winding can use either wet or dry material. In wet winding, the resin is applied at the time of winding by drawing the material through a resin bath. In dry winding, pre-preg material is used. The toe is typically applied by hoop winding or helical winding. In hoop winding, the toe path is almost perpendicular to the mandrel axis. Each mandrel rotation advances the material delivery supporting carriage one bandwidth, butting the edge of one band next to the previous band. In helical winding, material is deposited in a helical path in one direction, then turns around on end and returns in a helical path in the opposite direction. This routine continues until part thickness has been built up. To provide the desired mechanical properties of a part, combinations of hoop and helical winding can also be performed. Filament winding mandrels may be made of steel, aluminum, copper, or non-metallics, and designed to collapse or be dissolvable for removal from the part after curing. Dissolvable materials include eutectic and soluble salts, sand with water-soluble polyvinyl alcohol binder, low-temperature melting alloys, plaster, or thermoplastic foams. Pultrusion is a continuous process used primarily to produce long, straight shapes of constant cross-section. The process is similar to extrusion, except that the material is pulled rather than pushed through a die. Pultrusions are produced using continuous reinforcing fibers called roving that provide longitudinal reinforcement. Transverse reinforcement also is incorporated in the pultrusion using matte or cloth materials. The reinforcement is generally resin impregnated by drawing it through a resin wet-out station. A surfacing material is typically added afterwards. The saturated reinforcements are then generally shaped within a guiding or preforming system and subsequently shaped and cured through a preheated die or set of dies. Once cured, the pultrusion is saw cut to length. Material waste for pultrusion is low because excess resin is squeezed off the fibers and returned to the wet-out station. Pultrusions can be hollow or solid. Pultrusion dies may be fixed, or one may float, such as internal mandrels used in making hollow parts. The pressure applied can be hydraulic or mechanical. Although part cross-section is typically constant, floating mandrels can permit some variation. Pultrusion applications include bar and rod, pipe, tubing, profiles, ladder rails and rungs, truck and building panels, sheet and panel stiffeners, and supports of many kinds. Resin transfer molding, or RTM, is an efficient method of producing large and complex composite parts at faster rates than by other composite manufacturing methods. In one such method, a matched mold is loaded with the proper amount of reinforcement material, and the mold halves are clamped together. Resin is then pumped or gravity fed into the mold, infusing the enclosed reinforcement material. Air within the mold is vented as it is displaced by the resin. Once the resin fills the mold, the fill hole and vents are plugged. The part is then allowed to cure. Once cured, the mold halves are separated, and the part is removed. Resin transfer molding can also be done using preforms and may be accompanied by a vacuum assist. Molds may be either non-metallic or metal. Non-metallic molds are typically fiber-reinforced polymers. Their use depends largely on curing temperature and production volume of the manufacturing operation. Metal molds are used for high-temperature processing and to provide longer service life. Applications for resin transfer molding include automotive and aircraft parts, bath and shower enclosures, ventilation components, and machine cabinets. After curing, polymer matrix composites can be cut, machined, drilled, and otherwise fabricated by many of the same methods used for metals. However, because the materials are abrasive and brittle, the need to maintain sharp tools to prevent delamination cannot be overstressed. Although high-speed steel tools can suffice, tungsten carbide and diamond tip tools are often preferred. Also, coolant is often recommended to minimize heat buildup and to prolong tool life. Work-holding fixtures should provide proper part backup to prevent backside material breakout in various operations. Polymer matrix composites are typically cut with bandsaws, circular saws, and saber saws. Bandsawing speeds with high-speed steel blades range from 4,000 to 6,500 feet per minute at feeds of 6 to 12 inches per minute. With circular saws, the speed range is broader still, 2,000 to 10,000 feet per minute. Blade speeds of 2,500 strokes per minute are suggested with saber saws. Manual and machine routing have been effective with fluted carbide milling cutters and carbide-opposed helical router bits. In machining operations such as turning and drilling, speed should be somewhat greater and feeds somewhat less than for metals. For drilling, large positive rake angles are recommended to reduce the penetrating force and thus heat buildup. Drill flutes should be wide and polished to ease chip removal. Secondary operations, such as reaming and threading, can also be performed on composite parts. There are two principal joining methods for assembling polymer matrix composite parts: adhesive bonding and mechanical fastening. Adhesive bonding joins surfaces together by using a liquid or solid adhesive that resists interfacial separation between the two surfaces of contact. Adhesive bonding forms permanent joints. Surface cleanliness is critical for optimum adhesive bonding performance. All grease, mold release, and other contaminants must be removed from the contact surfaces or joint region before adhesive application. Abrading the region first is better still. Joint types for adhesive bonding include single lap, double lap, stepped lap, single overlay, double overlay, and scarf. Composite bonding adhesives are numerous and include epoxies, bismuth imides, acrylics, polyimides, polysulfides, epoxy phenolics, and urethanes. After the adhesive is applied, the workpieces may be placed in a fixture and then pressed together to remove trapped air and cure. Some adhesives cure at room temperature, but many require elevated temperature. Adhesive bonding can also be used to bond surface-mounted fasteners and bushings, thus combining adhesive bonding and mechanical fastening. Mechanical fastening involves the use of rivets, pins, bolts, and other fastener types to join composite elements together. Mechanical fastening requires precision hole making. Titanium alloy, superalloy, and stainless steel fasteners are often used, but polymer matrix composite fasteners are also available. Mechanical fastening clamping loads should be sufficient to close gaps, but not so much as to cause distortion or breakage. Let's review the material contained in this videotape. Composites are made up of at least two distinct intended materials: a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. Some of the primary matrix materials include polyester, epoxy, bismuth imide, phenolic, and polyimide. The reinforcement's function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles. Some of the most commonly used fibers are e-glass, aramid, and carbon, which is also referred to as graphite. These fibers come in many forms, including strand, tow, fabric, pre-impregnated or pre-preg tape, and preforms. There are numerous methods of producing composite parts, with the primary types being manual layup, automated layup, spray up, filament winding, pultrusion, and resin transfer molding. After production, composite parts may be allowed to cure at room temperature or with open-air heat assist. Composite parts are also commonly consolidated and cured in heat platen presses, ovens, or autoclaves. After curing, composite parts can be cut, machined, drilled, and otherwise fabricated by many of the same methods used for metals. Additionally, composite parts may be joined and assembled using adhesive bonding and mechanical fastening.